This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Right. Just come on. Okay, just a quick reminder that the first assignment is up on LMS. It's a series of exercises out of the book, focusing on sensors, actuators, input, output, and memory. So what we do today, and probably carry slightly over till next Monday, is important for the assignment. Okay? So in particular, some of the caching stuff that we'll look at. Okay, so where were we? We were looking at how memory is organised in programs. Okay, and there's basically two ways, either statically done, so a compiler chooses where things live in memory, or you can do it dynamically, where in runtime, some sort of operating system or some smart mechanism in your embedded system actually starts locating things in memory. Okay, so we saw that if you statically define variables or globally define them, basically what happens is a compiler sticks it in memory somewhere, and the compiler decides where that variable lives. So for instance, if you declare x outside of a function, it reserves a bit of memory for it. Likewise, you can declare it as a static variable which tells the compiler to go and shove it in memory somewhere of its own choosing. But if you define it as a static, there's a bit of inbuilt protection with the compiler, where it can detect if you're trying to use x out of scope of the function. Okay, the last thing we looked at, and we're going to analyse this in a bit more detail, is for variables that you create inside functions. So we know, or you should know, that variables that are created in C inside a function have just scope inside the function, in that they're not accessible outside of it. They actually are. It's just living in a memory spot, and some other function could actually go and look up that memory spot and grab the value of the variable. That's fine. But C, when you're trying to hide things with variables and stuff like that, right, because you're at a bit higher level than the direct hardware, C will prevent you from doing that. So variables that are declared inside functions live typically in an embedded system on what's called a stack. Now, a stack is just basically a block of memory that grows up and shrinks down. So in this case, what happens is you have an area reserved in SRAM for this architecture. So the architecture we were looking at had some reserved space for registers, some I/O registers, some external I/O registers, and then a big chunk of SRAM to store things and read things from as it's whatever it's doing, calculating, processing. So there should be a little, graphic here. What happens is the stack typically starts at the end of the block of memory and works its way up. So you can think of it as stacking up. Any variables that you need to store inside functions get stacked up on this stack, and it grows up in memory. When those variables are freed, in the sense that you get out of this function, so you don't need that variable anymore, the stack, should go the other way. So it should shrink. I don't know, I thought that it did. The animation shows it shrinks back down. Okay? And we have what's called the stack pointer, which points to the top of the stack. Now, by top of the stack, we mean the last element that was put in the stack, or on top of the last element. Okay, not the highest memory location is not the top of the stack, because typically the stacks grow up in memory when we lay out memory like this. And by growing up, I mean down. No, that doesn't make sense. But by going up in memory, I mean down in logical addresses, okay, or physical addresses too. Okay, so what about... Let's analyse some code. Okay, so this is going to show you the importance of, as a programmer even if you're a computer scientist or a software engineer for an embedded system, you probably have to know what's happening in the memory space with respect to variables. Okay, so let's put a little bit of code. Let's define a variable outside of a function. Let's set that variable equal to a hexadecimal number, and that's all that function foo does. It's pretty simple. So where is x located? So x, we know its value. Its value is just 20 hexadecimal. So it's an 8-bit number. But where is it stored? Where is it stored? So if it's declared here, it's a static variable in the sense that it has a fixed memory location. And it will be stored in the internal RAM. So we can look at the little memory mapping here at some point that's chosen by a compiler. So perhaps, maybe I can sort of write this very quickly down. If I can find my pen. And so that variable is, it's known where it is and it lives there forever. So we can find my pen. That's the next task here. Where on earth? Give me a sec. You've got so many wires in here. Or did I already get the pen out? Yes, I'm an idiot. It's here. Right. So, okay, so firstly, this x is now an 8-bit quantity. So if you define something as char in C, it's defined as ASCII, right? It's a character. So it's going to be 8 bits. It pads it out to be 8 bits. An 8-bit quantity. And where's it located? So 8-bit, it's stored in statically in memory, and it's at a spot chosen by the compiler. Once again, it's quite difficult to work out really where that lives. You've probably got to have some sort of real-time debugger that can fish out memory locations and try and find where that is, or disassemble the code, the executable, and work out via symbol tables and all sorts of things where that could be. Okay, that's pretty easy. So that's an 8-bit quantity. It goes and lives somewhere in memory, in the memory space. Okay, what about if we did the following? Dreaded pointers. So if I declare a pointer to char called x sitting outside of a function here, where does that live and how big is it? Okay, so firstly, that's going to be 16 bits. Now, it's important to know, well, where'd you get 16 bit from? Because of the architecture of this particular embedded microcontroller here, that memory locations are 16 bits wide. Okay, so it's a 16-bit address. So at least I know what that is, right? If it's an 8-bit architecture, that could be an 8-bit address, 32-bit, it might be 32-bit. So the compiler knows that that's a 16-bit pointer. Then what happens? So we know it's a 16-bit, but where does it live? It's statically stored again. In memory. SRAM, typically, I'll write SRAM there. in static RAM. And what happens? Well, then what we do is we assign an 8-bit, right, hexadecimal, 2 hexadecimal digits is 8 bits, 8-bit value to X. So what really happens is, somewhere in this memory space, X is living now, right, so living somewhere, and it actually pads it out to be X equals, oh, sorry, I should make it hexadecimal. Hexadecimal 0020, right? Because it's an address, well, it's a 16-bit quantity, you give it 8 bits, an assignment, it actually pads it out to be 16 bits, so it leads it with a couple of zeros. Okay, so it's stored statically in SRAM. Compiler decides, let's write some notes here, compiler decides where it goes, and the value it's given is 0020. So that's slotted somewhere into the SRAM memory space. Compiler makes up its mind. Okay, let's get a little more complicated. Let's define a pointer to char and a char. Let's make an assignment to the pointer and then dereference the pointer and assign that to y. Pointers. Don't you love pointers? So what's going to happen here? This is an interesting one. Okay, so what are these quantities? Well, 16-bit quantity. It's a pointer to char. It's a 16-bit addressable space. A char itself is just an 8-bit value. So we've got a 16-bit value and an 8-bit value. And what happens here is that if we are assigning 0x20 to x, that is now it's a memory location, right? That's a memory location now. And we're going to dereference that memory location and assign it to y. So what happens? Once again, these are statically allocated by a compiler. I'm just sort of jotting these points down. Statically allocated by a compiler, which means it lives in SRAM somewhere. You can put it that way if you want. Some fixed locations for those things. And the sum product, sum of all of this stuff here is that X, right, is being padded out now to 0x0020 because it's a 16-bit quantity. We're setting it equal to something, and we dereference it. We're actually reading a memory location. Okay, so this is reading the memory location 0020. It's very hard to see what I've ringed there. Oh, wow, you can actually see it on there. I can't. It's cut off on here. Okay, so what this operation does is it is loaded into Y the value of the memory location here, which happens to be one of the I/O registers. So you could perhaps read from an analog digital converter or something like that, which has its memory space mapped there. All right? So statically allocated because they're outside the function, and we're reading that value into Y there. This is 8-bit as well, I should say. All registers here are 8-bit, so that's an 8-bit value going into Y, and it's defined as a char, right, which is 8-bit. Okay, we might be getting a feel of things where variables are starting to live now. Let's look at another example. Oh, function, calling another function, global variable, kicking around. What's going on here? Where are these variables going to live? Let's work that out. Either they're going to be stored statically or they're going to be stored dynamically on a stack. I think it's pretty obvious here. This one here is static. It's a char, so Z is... I'm mixing my units here. It's 8 bits, right? It's a char, it's an 8-bit quantity, and it's static, so it lives in a fixed memory location determined by the compiler in the SRAM. Now what about these two here? They are declared inside a function, and functions, after they finish, what happens to those things? Kind of just go and just disappear, right? And you can never get them again. So these are dynamically put onto a stack. Okay, so in the memory space, what's happening here is you've got some fixed locations where those static variables are being shoved into, but then your stack here, if I may shade the area where the stack is, can get things popped on top of it, placed on top of it. Okay, pushed on top of it, I should say. Okay, and so because it's inside a function, these two things get pushed onto a stack. One is a pointer to char, so that ends up being, because it's a pointer, it's a memory location, so it's a 16-bit quantity. And then y is an 8-bit quantity. So that's it. That's where they live in the memory space. Z lives in a fixed location in SRAM, and it's 8 bits wide. And X and Y live on the stack, and they are 16 bits and 8 bits respectively they take up. All right, so now you're getting the idea about temporary variables that are created inside functions just get plonked onto here, onto like a little stack space to be used and manipulated and maybe overwritten. All right, last one. Let's do some real crazy stuff. Let's create a pointer to char. Let's create a char. Let's give it an address. Let's then dereference something. Set a pointer. Yeah, okay. So what on earth is happening here? In particular, what's this line doing here? So we can go through the analysis again, right? 16 bits, it's a memory address. If we're making it a pointer, it's a memory address. This is now, 8 bits. It's just a char, which is always 8 bits. And these are stored on the stack. Remember, stack is a dynamically created thing that the hardware is maintaining as it goes, typically. So this is an interesting one. So these things are pushed onto this, reserved on the stack as memory locations, right? X and Y. Now the interesting thing is X is actually set equal to the address of Y. That's how you think of that, right? The address of Y. Now let's sort of draw a little stack here, and pointer X is placed on the stack, and also that variable Y is placed on the stack at a particular location. So where's the address of Y? Well, it's here, right here, whatever that memory location is. Now, interestingly, that is there, and that is the top of the stack. So we can actually find where the top of the stack is because that was the last, Y was the last thing that was pushed onto the stack, okay, in order to do our manipulations or whatnot. And so that is the actual address of the stack. Then what happens here is we then load Y, because we dereference it now, so we load Y back with a different value. Okay? So there's some funny stuff happening here, right? We can actually start mucking around with what's going on in the stack, sort of indirectly even, by doing this. The summary of all of this is, if you really don't want to read the code, is that Y becomes just OX2O. Okay, the stack pointer becomes OX2O. Okay.
Are you saying the Y address becomes 0x20 or the Y element?
Okay, so this is the address. This is the address of Y. That's the stack pointer loaded in X. What does this line do? Yeah. what does it do? It sets, right, that's an assignment. So it sets that this to be equal to that, which is, this is really y, right, to be equal to that. All right, which is an 8-bit quantity, and that's okay because y is an 8-bit, declared as an 8-bit char.
The address of y is 16 bits, right?
Sure.
And x is 8 bits because it's char?
The address of A, sorry, well, no, this is 16-bit quantity because it's a pointer into 16-bit memory space.
So x is also 16 bits?
Oh, that's a good point. It depends on, C might have a whinge about that, or it might pad it out with zeros. That's a good question. All right. Last one. Where do these things live in memory? I think we can probably get this. UN16 is just an extension to the integer type, makes it 16 bits unsigned, and these both live on the stack. And this is statically determined address and statically allocated, I guess, by a compiler anyway, when it's built, and it is 8-bit as well. Okay, so getting a bit of an idea about where these things live is important because I'm going to present to you a couple of examples where things could go wrong, but the computer scientists would say it's all fine. So let's have a look here, or the programmer, I should say. So here's a little program. I know it's got some bad programming practice in the sense that there might be global variables and such like that, but whoa, what does this program do? So not a hell of a lot. So it calls the main program function, right, calls some sub-function here, passes an argument into it, creates some variables, right, reserves some memory space for them, does some calculations, returns the location to that, and it becomes a pointer to int. Let's have a look at this in detail. So that first statement there, obviously, it's a statically allocated thing. Go and shove the value of 2 and some variable x in some location. Here's an interesting question. How do you actually pre-assign variables? How do you pre-assign a variable? Typically, when you turn on a microcontroller, everything's junk in it. All the memory space is just yuck. How do you actually pre-load something? You need to initialize it somewhere. Yeah, and you can't do it in code necessarily, right? Well, you can't do it in code. So what you do is you, in the binary itself, right, one of the first things it will do, the bootloader, when it actually turns right on, is it just pre-populates the memory space with whatever's needed. Okay, so it would pre-populate a particular location with a value of x equals 2 before you start ticking through program counters and all that sort of stuff. Okay, so what happens here? Let's have a look. Let's start here. So when you make a function call in hardware, what really happens? Well, you need to know, you basically need to save the state of the system. Okay? Because the idea is whatever happens here on these dots should not be destroyed by what happens here. Okay? Now in the hardware, what happens is when we issue a function call, the program counter, so where we are actually, what instruction we're up to in terms of sequential instructions, the argument, which is just a constant in this case, and then when we get into the function here, Z all get pushed onto the stack. Okay? We need to save where we need to come back to, which instruction we're up to. We need to pass an argument in, 10. Right? You've got to store these somewhere. You can't just leave 10 hanging around to go and use it later. And also we need to create that variable. So 3 things are basically at a minimum, pushed onto a stack, onto the stack there. Okay, so this code will actually work, right? Well, this code will pass in 10 and it'll multiply by 2 and all of that. It's all good. But there is a slight problem here. What happens if, as this procedure is being called, right, as it's being called, what happens if an interrupt occurs? We'll talk a bit about what interrupts are, but an interrupt basically can mean that as you are jumping to other bits of code and doing the processing needed to do that, so pushing things onto a stack, saving the state of the system, you might have to jump to another part of the code and save the state of everything then, and then maybe jump to another part of the code and save the state of the system. So this code works fine, but it actually has a bit of an insidious error. What happens here is, think about the order of things. You push the program counter onto the stack, you push 10, you push Z. You give Z an assignment, okay, it's 20, big deal. But then you return the address of Z, which is a pointer to int. All right, so that is the stack pointer address. It's a pointer to the topmost element in the stack. Now that could be that's a really bad thing, because what happens if just before, or well, in any sequence of instructions, if you get an interrupt, the stack gets added to basically, right? So things can start going crazy if you're returning a stack pointer down here. Later on, you may do some calculations where the variable where you thought it was may not really be there anymore, right? Or may contain a different value. Okay, so we have to be really careful with returning memory addresses, particularly to variables that are created on a stack, because the stack is a moving, living thing. There, things get put on and taken off at all different times. Okay, the last one is the best. I've saved the best for last. This piece of code may make an aeroplane crash. It may make something blow up. It may make someone's life support system turn off. It's that bad. What happens here? Okay, let's start down here. So we've got a nice little 8-bit statically allocated variable. We're going to set it to something. Good. And then we're going to call a function with a 16-bit number in it. Okay, so up to here, we go up to here, 16 bits, good. Create a new variable on the stack, y. Set it equal to the address of x, dereference x. Then, if x is greater than that, call itself. So it's a recursive function. Now, what this function does is, it's essentially, well, it's calling itself with the same argument over and over and over again. So it's pretty boring. But every time a function is called, so it's calling itself, and it's decrementing x by 1. So it keeps doing this, right? Calling itself, decrementing x by 1. Now, x starts off as this address here, which happens to be the bottom of the memory space, right at the bottom of the memory space here. And we're decrementing it by 1 each time, and then doing some stuff with it. So we're actually going up, 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 up in memory. Up as in decreasing the memory value by 1. Now what happens here is, oh, that's easy. We'll just put a stop so that once we hit x hits here, right, we don't want to start writing into registers, because registers are dangerous. Registers control things. Registers explain what instruction to run next. They're controlling various actuators and stuff. If you write into a register, right, some bad stuff can happen. So we're just going to put in the loop here a little condition to say, hey, as long as x is greater than that, so we're still in this memory space here, then keep iterating and decrementing x by 1. And so you would think this is fairly safe, right? This is quite safe. It will run, and it will give you some appropriate output. But if you don't understand how the hardware works, and you go and try and run this, you'll probably kill someone, right? Because it's going to go nuts. What's going to happen? Every time we issue a function call, we push some stuff onto the stack. We've got to save the state of the system. So this function call here, what does it do? It pushes things onto the stack. It pushes the program counter. It pushes the argument, which is a 16-bit number. And upon entering the function, well, it's got to create some space for this new variable y. So it also pushes y onto the stack. So every time foo is called, those three things happen. Push the program counter, push the 16-bit quantity, and push y. Okay, the program counter here, 16 bits. It's a pointer into memory. It's a 16-bit addressable space. 16 bits for the that number there that has to be stored. And then y, what's y? Y is just a good old char, so it's 8 bits. So what's happening? Well, how many bytes is this? 5 bytes are being pushed onto the program counter, onto the stack every time. So essentially what's happening is, even though we're decrementing x by 1, right, the memory location up here, we're going up, 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 up. What will happen is we'll actually leapfrog that. We'll never get, well, we probably won't get there. It depends on if it's a nice multiple of that. So typically what will happen is it will start encroaching into the I/O, the external I/O register space, this little program. So to the programmer, hey, it runs fine. It'll never write into that protected space. But for this architecture, knowing that it pushes certain things, and maybe even more, some architectures push more things onto the stack, you will actually end up writing into the, accessing the memory space there, which is dangerous, very dangerous stuff. Okay, you will be writing into there actually because you're making an assignment on Y. Okay, so that's how I have to harp on about how dangerous writing code is for an embedded system where you don't know the architecture for it, particularly if you use recursion. Recursion is dangerous. Okay, compiler won't catch that. Probably not. All right. So the stack is that system where it's very simple. It just puts things on and takes them off as it goes to do calculations. An operating system, so immediately we're talking not bare bones, bare metal system, typically allocates memory to what's called a heap. And we're not going to focus on the heap. What's the difference between the stack and the heap? The heap is a much more complex object. If you've ever used these functions here, malloc and free, what they are doing is accessing a heap. What's a heap? It's like a block of free space you have, and the operating system, if you call the function malloc, the operating system looks for a spot in the heap to put your variable. Okay? So the operating system actually has to know what's populated in the system and where to put stuff. So what that means is you get problems. If you really get down to the low level and start mallocing stuff all over the place but forget to free it, you run out of memory. Who cares? 16 gig of RAM, who cares about a few bytes here and there? But when you're talking about embedded systems that may only have a few kilobytes of RAM, you're dead, basically, right, if you don't get rid of that stuff. Also, the memory becomes fragmented. So you have bits that are sort of statically reserved by a compiler. Dynamically, you've got the heap, which are these spots where you can put stuff, and it starts getting completely fragmented. You want a big block to go in there, but there's no spot for the block. So it may have to segment it or something crazy like that, which is then another layer of complexity. So typically what happens is the OS does garbage collection. It frees memory, right? If you ever look at your task manager on a PC or activity monitor or whatever, and you're watching it, the memory is going up and down all over the place. What's happening is you've got processes that are sitting there and freeing memory and such in the background as it goes. It's great for a computer, terrible for an embedded system. Why? because it makes predicting stuff impossible. A real-time task becomes no longer real-time if there's a controller there doing memory allocation and freeing while you want to actually do something, right? You've got to pause and wait for some memory allocation technique to be going on. Okay, so we won't talk about heaping. We don't talk necessarily about OS determined dynamically allocating, because this doesn't typically happen in embedded systems because it's too difficult to predict. Okay, so I want to talk a little bit about memory hierarchy. In particular, this is probably important for the assignment. Talk about caching. The idea behind caching is the following. There's a hierarchy of memory, and the best way to read this diagram is almost from left to right, fast to slow. Okay? So there's a hierarchy of memory where accessing stuff that's close to the CPU, like registers on the CPU, super fast, great. You haven't got many of them. For an embedded system, you might only have 8, 32 maybe if you're lucky, not many. So what happens is then you've got to fall down to the next level of the hierarchy, typically SRAM. And we're going to call that the cache. So that could be a stack or something like that, but a cache is the next level we're going to look at. Then if something's not in the cache, you have to then hit the main memory. And so you're looking at DRAM. Now, SRAM doesn't have good density to it, so you won't have lots of it, but it's super, super fast. The way of accessing it's really quick. DRAM, that's less reliable. It needs refresh controllers, all that sort of stuff. And so therefore, it's bigger, but it takes longer to access. And finally, if what you want, think a variable, you look for it in SRAM, it's not there. You look for it in DRAM, it's not there. You may have to find it on flash memory or a disk. It may have been paged out in virtual memory or something like that. And that's the slowest of the slow. This flat hierarchy here assumes the same address space for everything. You actually have no idea what's what. You write to a memory location, and sometimes it might be an external device, and sometimes it might be a bit of SRAM, and sometimes it might be DRAM or whatever. But the idea is that you don't necessarily know where you're writing. Okay, it's not blocked as such. Okay, it's just a bunch of stuff all thrown together. Sometimes you'll be accessing this, sometimes that for a given location. Typically how we divide the memory space up is like I showed you last time, with physical and logical addresses. And so these are the physical elements, and then they would have a logical addressing space. Okay, between certain locations, that is the SRAM. Between certain locations, that's DRAM, and then certain locations, big locations, that's the disk. Now, the nice thing about that is that's much easier to control the timing. Back here, if I want to find X, right? And obviously the processor knows where X is, and if I want to manipulate it, it goes and finds it. And so it looks in its registers, X isn't there, looks in the SRAM, well, it's not there. Maybe it'll find it's been stored in the DRAM, okay? It's impossible to know the timing of how long that will take, because what happens if it was actually in the cache? It'd be quicker. What happens if it was actually stored in the register? Be quicker still. This method of segmenting the memory space makes much more sense from a timing perspective, because I know if I access something in a certain range, it's going to be in the DRAM range. Aha. It's going to be 10 milliseconds to access it or something, right? Well, that's more disk, but 10 microseconds. If it's in SRAM, hey, I know it's in that range, it's going to be 10 nanoseconds to access it. So I can control the timing much better by knowing what I'm accessing at a particular time. Okay, but it does mean you are constrained by the architecture. So if there are lines here where that's the only space that you can use for SRAM, that's the only space you can use for DRAM, nah, you're stuck. If you want to expand things, it's very difficult to expand it. You can't do it. The hardware is actually controlled, you know, it's fixed. Here, because everything's just kind of all in the one space, and sometimes it's SRAM and sometimes it's DRAM, you can just tack stuff on the end and it doesn't matter. Okay, I'm going to talk about something that is important. It's actually important for the assignment, but it's important because it's something that's talked about lots, but maybe not understood so well. And this slide kind of, has a lot going on. The idea is, think you've got variables X, Y, and Z. Okay, and they can live anywhere. They can live in SRAM, they can live in DRAM, or on the disk if need be, if they need to be manipulated to be put there. So the idea is, stuff that's accessed quite a lot, that's either in main memory or on the disk, why don't we go and store it in the SRAM? Because accessing the SRAM is less of a hit in time than it is to go and grab it from either of these two slow things down here. And so that's the idea of caching, right? And the English word to cache is hide something or store something, and that's exactly what cache means. And the simplest form of caching is what's called a direct mapped cache. Now, this is like a really formal way of showing what happens, but I think I'll do it in terms of colours because it's nicer. So I'm going to just make this up as I go and do it in colours. And I did a rough sketch of my idea of how I'm going to do this. So the idea is, let's say you've got a big memory space. DRAM is cheap and plentiful, and you've only got a little bit of SRAM, but it's really fast to access. So the idea is, if this is your main memory, big main memory, and this is your, let's call it DRAM and SRAM. The idea is, you can't fit all of that into that, otherwise why would you even have that? So we're going to fit a subset of the DRAM into the SRAM. How do we work it out? What do we put in there? We're going to put a particular subset. So let's block this up. Let's make this into blocks, and I'm going to make them coloured blocks because we're segmenting the memory space. So this is blue block. What do I have for colours? These two are now black. What have I got? I've got a green colour. And I've got red. And we're going to keep doing that. We're going to use 4 sets here. Okay, well, these are called sets. And therefore, if the memory space we repeat, right? There's blue set, the second set of blue. Then there's black set, and so on and so forth. We divide it up into sets, the memory space like that. And at any one time, we have this little area of SRAM that will store something called a tag, and then the actual data itself. So how does it do it? So I can't fit all these things in here. So what I'm going to do is, for a very simple direct mapped cache here, what I'm going to do is I'm just going to store one of these double blocks of blue into here. Now, which one am I going to store? Well, it depends on which one was last accessed. So in this case, let's pretend that this one was the last one accessed. And it's going to go in here, so it's now blue, and we're going to store those 2 blocks this way. There's my 2 blocks. They've been lumped into SRAM, and I'm going to give it the tag 0, 000, let's say, because it's the first of all of these, of all the blues. Okay, so it's the first tag of the blues. Now the black ones here, actually let's do something different. The black ones are those black ones which I'm going to store. So they will go into here, into this set, but this will have a tag of 1 because it's not the top one, it's the next block. And that goes into here. And likewise, so this would be the green set, or set 3 if you like, and that's got a tag of 000 because it's not the one that's going to be further down in the memory space. And the red one here will go into here, and this will also be tag 000. It's the first one of the red tags. So the idea is you get these things are stored in here. So what happens is, if you can imagine now the CPU perhaps on this side, it needs to access something in memory. What it does is it breaks up the memory address in terms of set, so think colour for set here, and tag. So memory address space now, the upper bits are separated into set number and tag number. And what you can do is you can do a very quick lookup here and find if that memory address is actually already stored in the SRAM. If it is, it's really easy to grab because, well, you can just get it straight away. But what happens if it accesses, right, it knows which set to look under, but it's the wrong tag that's in there? Then a mechanism comes along and basically grabs the other tag that you're looking for, puts it into here, and overwrites the tag number. So you can see now how multiple blocks of colours, right, they're all variables and things stored in DRAM, can be pulled into this tiny SRAM, identified by its set number, so the colour, and its tag number, which is like the ordering within the set. Or maybe that's the best way of saying it, I don't know. The order of the set. So that's tag 1, tag 0, tag 0, tag 0, tag 0, tag 1, etc. Okay? And that's basically, that's how the simplest form of caching works. And most decent processors have this direct mapped cache because it's too costly to access DRAM, and even worse, if you don't have DRAM and you have disk hanging off here, disk takes forever to access as compared to SRAM. Okay, so that's a direct map cache. There is another picture, obviously, here that goes into a bit more detail to show you how the tag and the set work to basically identify which set, which colour, and which tag is the valid tag there. All right. There's also a different type of caching which starts getting crazy called the set associative caching, a cache. I won't talk about it too much because it uses some quite cute stuff called content addressable memory. Basically, if you look at these two pictures, the only difference is now you can have multiple things living in the same set, okay? So different tag numbers in the same set. Ooh, it starts getting messy. So you can imagine it would complicate my little diagram here. I'd have to have, with blue, I could maybe have blue tag 000 and blue tag 001 in the same set, okay? So you've got to do a couple of lookups, basically. You've got to look up the set and also then find the tag within the set, and that's a complex algorithm to do that. There are people that spend their entire working careers developing algorithms for cache access on processors, okay, and research and all of that. It's a crazy area when you get into it. So I won't talk about it too much. How do you actually replace stuff in the cache? In this case, you need a replacement policy. And there are a couple of policies for doing it. So least recently used. You've got to have some algorithm that's keeping track of the one that was used the furthest in the past, and you replace that, or first in, first out. Okay, so there's a couple of ways of replacing the sets in the cache. And as I said, it gets super, super crazy messy. Okay, I'm going to give you a quick preview of the hardware. If you're in the Friday workshops this Friday, you're going to start programming the the MyRio board. If you're in the next week's Monday till Thursday, you could do it next week. That's the architecture of that, the Xilinx processor in there. That's the big Xilinx thing there. It has two things to it. I've said this before. It's a very flexible system. If you could ever get your hands on one of these, they're great to play with. It has a standard multi-core, dual-core processor. It's an ARM A9, sorry. It has real-time Linux on there. So it's got an overhead of an operating system. You can do what you like in there. It's doing all its memory management and all that stuff on top of it. So it's an embedded real-time Linux system. You also have this Arctic7 and FPGA, which is a hardwired logic component in there. And that's for real-time stuff. Remember, this is real-time Linux. Real-time is in inverted commas because there's an operating system. Stuff is happening at the same time, and it's hard to predict what's going on. This one's really cool because you can actually pre-configure it with something called MicroBlaze, which is a microprocessor that's implemented on an FPGA. So it actually gives you a microprocessor with no operating system. It's just sitting there for you to play with, right? It's saying, feed me some instructions, right? It's not just sitting there with a prompt where it's still doing stuff in the background. So that's called a bare metal system there. And that's the most fun to play with because that's a real embedded system. Okay, so as you look at the architecture here, it kind of shows you how you've got the programmable logic and then you've got the ARM stuff sitting in the middle here. This is all the stuff that you can program on the fixed personality FPGA to give you real-time performance. So you've got CAN controllers, right, for like complex networks and stuff like that, I2C, SPI. It's crazy. So you're going to really enjoy programming this thing next week or Friday if you have it on Friday. All right. I think we'll leave it there. We'll have to continue next week with input-output, which is not as difficult as thinking about memory mapped stuff, so we should be able to get through it fairly quickly. All right, and if you've got questions, come down and talk to me now. I'm happy to talk to you.